Hi everybody, I'm the greatest living inventor, and today we are doing my invention, wildfire spark drainage. So I'll write it down. Wildfire spark drainage. Okay, so it's the third time that I'm recording, so I hope this time I will be on time. So I will draw less and talk more. Sorry. So problem outline. In the interesting documentary, mega fires engulfing. I'll just change the marker because I don't like the way it writes anymore. Thank you. So I'll just write it down again. Wildfire spark drainage. Okay, we did already, I made an invention against wildfires. This is my second invention against wildfires. It's completely different, and it doesn't use water. Okay, so problem outline. In the documentary Mega Fires, engulfing forests and cities, okay, this is by NHK. It's Japanese, 2020. Okay, it's a documentary. Okay, so in this documentary, I'm writing the name because we'll talk a lot about it. You can download it from docuwiki.net. Okay, it's by MV Group. This site is by MV Group, and I download most of what I see is from here. So in this documentary, 3 experts explain 3 spreading mechanisms of wildfires: chimney effect, fire tornado, and fire cloud. Okay, I'm erasing. So in this documentary you have chimney effect, fire tornado, and fire cloud. And these are three mechanisms of the wildfire spreading. You can see this, all of this in Wikipedia, also in this documentary, but also in Wikipedia in wildfire hashtag physical properties. I will give you all the links in the description. Okay, so it's I'm erasing the headline. You can see this also in Wikipedia. Wildfires, hashtag physical properties. Okay, the same three. So my proposed solution tries to countermeasure all the three. Okay, solution outline. I'm not writing this because this is how I run out of time. So I'm just, this is 6 minutes and 30 seconds already. So I'm just describing. This was the problem outline. Now the solution outline. The solution outline, I will just read. The coral is a honeycomb shaped fire break with telescopic flagpoles. We'll talk about this in detail. The fire screen is a aluminium foil raised like sail. And the chimney funnel to ducted fan with spark arrestor, diagonally rise branches and disperses. And for lightning rod, fire cloud earthing using mortar that shoots a harpoon with a copper wire rope. Okay, so I know it's like Chinese or Greek to you, but I will explain it soon in detail. Okay, so the problem in detail, the experts in the documentary, the experts from Missoula Fire Sciences Laboratory in Montana, USA, and from University of Alberta, Canada, explain these three problems. Problem 1, thermal columns. Okay, so this is called, it's in the documentary, but now I'm elaborating. You know what, I will not elaborate, I will just read it because I'm afraid to run out of time. So the first one, the problem 1, is thermal columns. Thermal columns. This is problem 1. Cool air coming down, flattening and pushing forward and spreading the flames. In Wikipedia it's called stack effect. Okay, so if you look in Wikipedia, it's called stack effect. And if you look in the documentary, it's in minute 17:25. explained by research forester Mark Finney. Problem number 2, fire wheels. Okay, so this is called fire wheels. Fire wheels. And it's tornado-like flames. And this is in Wikipedia, it's called fire wheel. And it's explained by, this is problem 2. And this is explained in minute 20:50. Okay, this is in Wikipedia. This is in Wikipedia. Fire wheel, and it's explained by research mechanical engineer Sarah McAllister in minute 19. Sorry, I wrote the wrong number. Sorry, in minute 19. In the documentary. And the problem number 3 is a pyrocumulonimbus cloud. Okay, and this is also if you want to look in Wikipedia, it's cumulonimbus flammagnetus. Okay, so this is in Wikipedia, and it's a soot cloud that can cross a river and ignite trees on the other side by lightning. So in Wikipedia it's this thing, and it's explained by professor of wildland fire Mike Flanagan in minute 20:50 in the documentary. Okay, so so this is the problem in detail. Okay, and the reason that I'm writing the problem in detail is because someone might say, well, you found the solution, but it doesn't answer the real problem. So no, this is the real problem. These 3 things are the real problem in wildfire. Okay, so I'm raising this and I'm writing the solution in detail. This was the problem in detail. Now we go to the solution in detail. Okay, so solution in detail. And we start with the corral. Okay, so the first thing to do is to divide the whole forest into hexagon patches with a side length of maybe 1 kilometer, and on the outer lines of the hexagons to cut down the trees like fire break. Okay, so we have let's say this is like a honeycomb structure. Now we are looking at the forest from the air, from above. So this is what it will look like after we do the honeycomb structure. And every black line that I'm drawing is a fire break. Fire break. So you should see in Wikipedia what is a fire break. And this is the structure, forest from above. Okay, so and every one of these is full of trees. Okay, this is a tree. This is a tree. Okay, so you understand the principle. So every one of the hexagons is filled with the trees. Okay, and so from a bird's eye view from above, we see the gaps. These are the gaps. Every black line is a gap. And we see the gaps in the trees look like honeycomb structure. Okay, so and every black line is a fire break. Okay, a path without trees that we cut down the trees. Okay, in this way we can isolate and sacrifice the hexagon terrain compartment where the fire started. Okay, let's say if a fire started here, on fire, then we can say, okay, we give up on this this one. So here everything will burn. But we save the rest. All these are protected, are fine. So because we can isolate with what I will explain in the corral. So in this way we can isolate and sacrifice the hexagon, a terrain compartment where the fire started, but save the rest of the hexagons. I will call the hexagons cells, like in a honeycomb. Along the borders of the cells, we prepare in advance telescopic flagpoles, a little higher than the treetops, evenly spaced, like maybe every 25 meters. The poles are normally extended. They are just telescopic for maintenance purposes. Okay, so Wikipedia, flagpoles. Okay, so if we have flagpoles, let's draw them in purple. Okay, this is the flagpole. Like normally there is a flag here, but we don't need a flag. And you know how the flag has a rope, so think about the rope. We need the rope for later. So we have one flagpole and another flagpole, and they are telescopic, but we don't care about this now. It's just for maintenance. All the time they are up. Okay, so these are flagpoles. Okay, now we are talking about the fire screen. Fire screen. And this we will draw in another color, let's say in the magenta. So the fire screen is, I will read and then I will draw. So on these flagpoles, instead of flags, we raise the curtains pole, which is a steel wire. Okay, so it's like a curtain that you have in the shower, on which the curtain, which is a aluminum foil sheet, is hanging. Okay, so it's like we have here a wire, and this is the curtain pole. Okay, and on the curtain pole, just like you have in the shower, rings on a pole that you can put a curtain on. So here there is a curtain. Okay, so there is a curtain. Okay, this is a curtain. Okay, so which is a aluminum foil. Okay, the curtain is aluminum foil. Okay, so we have like these two poles. Okay, so imagine these poles are in purple. And we have such poles every 25 meters. Okay, like I cannot draw all of them, but you understand that there are poles along Okay, so I drew this only on one hexagon, but it's in every hexagon. We have the potential to put the curtain. Okay, so this partition between two neighboring cells, okay, so it's a partition like between this cell and this cell. There are curtains here. We look from above. This is we look from the side. So this partition between two neighboring cells should be prepared in advance and operate by remote control, without the quote, sorry, by remote control from the control center as soon as the camera, closed circuit TV or drone or a satellite locates the fire. So as soon as we locate the fire, we pull up the curtain like a sail. Okay, this is like, imagine this like sail. It unfolds, it's folded, and then it unfolds. Sail is on the other end, it's from the above from the top to bottom, but here it's from the bottom to the top. Okay, so we can install a pulley and a counterweight that drops, released by a small actuator, and the weight is tied to a rope that raises the curtain pole, this curtain pole, as the weight falls down to the ground. Okay, so if we have, like I told you that, remember the flag in the flagpole has a rope that you can pull the flag up. So the same rope, if we have here a pulley, okay, this is a pulley, and we have a rope, and this rope has a weight, rope with weight, and when the weight goes down, the rope goes up. Okay, and the curtain, there's also a weight here, and the curtain goes up when the weight falls down to the ground. The curtain itself can be stored folded inside a protected groove. Okay, so the curtain is stored here. There's like a groove. Okay, something like this. Okay, I don't know how to draw this, but it's folded inside the box groove. Like we have grooves in the walls of the house for electric cables and protected in plastic tubing. So again, when the signal from the control center arrives, then the counterweight from the top of the flagpole is released and falls to the ground. Let's say there is an electromagnet, and when the current stops, the weight falls to the ground, pulling open the tubing and raising, unfolding the aluminum sheet. Like that in the kitchen, but double the thickness and a lot bigger in area. And this happens in every section along the outer border of the cell in which the fire was located. Okay, so every cell has this, but in every cell it's in the groove. It's not activated, but in the cell when it's activated, then we, along this cell, we activate the curtain. Okay, the corral, which is made from curtains. And this happens in every section along the outer border of the cell in which the fire was detected. The aluminum foil is light, strong, and reflects heat, and is resistant to fire. For example, this is how you cook potatoes in a campfire. Okay, so you can see in Wikipedia, outdoor cooking, hashtag other covered techniques. I will give you the link in the description, all the links in the description. The corral, which is made up of fire screens, fire screens. Okay, each one like this is a fire screen. There is a fire screen here, and the fire screen here, and the fire screen here, fire screen here, fire screen here, all around. And also in the other cells, but it's not activated in the other cells, just in the cells where there is a fire. The coral, which is made up of fire screens, protects from burning embers that fly in the wind. Okay, the fire, let's say the wind is going this way, so the fire gives embers, hot embers, that if it gets into here, then it starts a fire here. Okay, so we don't want this, so this is why we make this curtain against the hot or burning embers. Okay, so once this coral is deployed, the firefighters have about half an hour to get there with the next part of the solution, which is the chimney. Okay, so now I will write about the chimney. Let's see how we are with the time. 32 minutes, not so good. I'm erasing everything and I'm explaining the chimney. Okay, so the next part is the chimney. Okay, so imagine we have this hexagon, this cell. Okay, this is the cell from the side. Okay, I hope you can see it. It's not in my drawing. It's not good. It's not hexagonal, but let's say. Let's make it hexagonal. Okay, so this is more or less hexagonal, and this is from the side. Cell from view from the side. Okay, so before this we had a view from above. Now we are looking from the side. So there are trees here. Okay, trees. And there is also a fire. Okay, so there is a fire here and fire here, and there's in this cell, this is the cell with the fire. So the chimney is basically a long hollow metal pipe. Okay, so basically it's a long hollow metal pipe. This is the chimney. And the firemen put the entrance end. This is the entrance end of this big pipe in the corner of the hexagon, the cell, toward which the wind is blowing the strongest. Okay, let's say here is the wind is like this. Okay, so we put the entrance. Okay, this is the entry. This is the exit. So the firemen put the entry close to the cell wall where the wind is trying to bring the fire. Okay, the wind is bringing the fire to here. So the firemen put the entry of this tube close to here. Towards which the wind is blowing the strongest. The exit end of this big pipe is high in the air at a safe distance above the tree tops. Okay, remember here there is a path. This is the fire break. And here is another trees, like another hexagon filled with trees. So we need this, and the trees are in this height, let's say. So this tube, this long hollow metal pipe is in not straight and not up. It's diagonal and it ends above the trees. Okay, imagine it a little higher. The exit end of this big pipe is high in the air at safe distance above the treetops. So the exit end is supported by telescopic supporting beams, or if this cannot be done, then on a large ladder. Okay, so here anyway, the supporting thing should be made from light and strong aluminum because it needs to get to the location using a helicopter. The chimney takes in air from the burning cell, which means smoke with firebrands, hot wood ember. Okay, remember we have these embers. And here on the other side there are no embers. So only on the entry end there are embers. Here there are no embers. The chimney takes in air from the burning cell, which means smoke with firebrands, hot wood embers, and other burning materials, which can start new fire spots. And then the chimney puts out hot air that is without any burning materials. This is done by a centrifugal spark arrestor. Centrifugal spark arrestor. Okay, so this is also something you should see in Wikipedia. And let's see what time it is. 40 minutes. Okay, so we need to hurry. Okay, so now we'll see how this is made. Not what it is, you should see this in Wikipedia. I'm just explaining where it fits in the big picture. So, now we are going to roll the barrel. Roll the barrel. Okay, so the barrel fits in here. Okay, this is the barrel. Barrel. What is the barrel? It's basically it's the centrifugal spark arrestor and also a ducted fan. Okay, the barrel is what I call the active part of the chimney. It contains both ducted fan plus the centrifugal spark arrestor. The barrel is what I call the active part of the chimney. It contains both ducted fan, which are just static metal blades that rotate when the barrel rotates, and the spark arrestor, which is also just static metal blades, only designed so that there is a space at the center of the barrel. Okay, so if you look at the barrel from the side, okay, a barrel from side, then it looks like this, and there are metal blades, and in the center there is the centrifugal spark arrestor, which is also metal blades, and in the center there is it's hollow. Okay, so basically this is what it looks like. You should see more details in centrifugal spark arrestor in Wikipedia. Sorry, I'll just drink something. Okay, so almost 45 minutes. Sorry, we need to really hurry. Okay, so this is the barrel. Between the fan and the spark arrestor, the inside of the barrel should get narrow towards the center. This is hollow. This is where the air is coming out of the exit. The barrel is here, but whatever comes out from here, this is this hole. This is the clean air, hot air, but without any burning embers. and it goes from out of the chimney. The whole barrel needs to be rotated from the outside. So it should be close to the ground, which means close to the entrance hatch of the chimney. This is the entrance, this is the exit of the chimney. I think it's easiest if that part lies horizontal on a special conveyor belt. The belt is small and needs to be able to survive the high heat, okay, because inside the barrel there are stuck the burning embers, okay, so inside the barrel, so the barrel gets very hot. It's metal, so it conducts the heat, so it's very hot. So in here there is a conveyor. Let's draw this in purple. Okay, so this is a conveyor belt. Conveyor belt. Pretty sure you cannot see this. It's too... No, you cannot see this, so I will do this in another color. Okay, so in brown. So this is the conveyor belt. I'm not doing this properly, it should be here. Like this, okay, from the side. But from here, this is the conveyor belt. And we will explain what we want from the conveyor belt. Okay, so it's like, it's not drawn like this, it should be rotating like this, into the whiteboard and out of the whiteboard towards you, and in and out. Okay, so I drew it from left to right, which is not correct. It should be left to right from the side, and here it should be like this, but I don't know how to draw this. Okay, so I'll draw this again, like okay, so okay, here is another small wheel, and this is a continuous wheel, and here is also, we cannot see the where it continues, but it continues. So all this is the conveyor belt, and it's under the barrel. Okay, so I hope you understand more or less what I'm trying to do. Okay, so okay, more or less. I hope you understand more or less what I tried to draw. It's a conveyor belt that rolls the barrel. Okay, so I think the easiest way is if that part lies horizontal on a special conveyor belt. The belt is small and needs to be able to survive the high heat. So maybe we can use high temperature mineral wool. Wikipedia, mineral wool, HTMW. Okay, so this is mineral wool. HT, high temperature, I guess, mineral wool, MW. This is in Wikipedia. Sorry. In order to take in the air, the chimney needs to initially use the heat-resistant fan. Okay, here it has the fan. But soon afterwards, the suction of the chimney suck in the air by itself, like a real chimney. Maybe we can, at that point, use the energy of the hot air rising in the chimney for the conveyor belt, if it is run by electricity. This is much preferred to start with the battery and then produce your own electricity, because bringing a small diesel fuel engine for this will require a close by tank filled with flammable fuel, which is dangerous. The conveyor belt is there because we don't want the heat from the barrel to get by conduction to the engines of the rotation and to ruin them. Okay, here is this is connected to an engine, but if we put this axle directly in touch with the barrel, then the engine burns. Okay, so this is why we need the conveyor belt, which is heat resistant. Okay, 53 minutes almost. In order for the batteries not to explode, the initial power not to explode, the electrodes should be far away from each other and not overcharged. About cold temperature, we don't need to worry. So this I get from Why Do Batteries Explode? This is from BBC Science Focus magazine. Why do batteries explode? I'll put it in the links. Last but not least, I wish to explain that the chimney is not going straight up. Okay, it's not like this. It's like diagonal. It's not like straight up. Because if it is going straight up, it might cause problems number 1, chimney effect, and problem number 2, fire tornado. That's why the chimney needs to be diagonal. So the entrance is on the ground level, but the exit is much higher. And also the exit hatch should branch out, like maybe 3 exit hatches. Okay, so we have, this is actually one exit and another exit and another exit. Okay, so it's like they're on the same level but branched, like to here, and here. Okay, on the same plane. I tried to draw this, it's not very good. Like maybe 3 exit hatches, all of them pointing sideways, parallel to the ground, high above the treetops, like maybe twice as high, pointing away from the burning cell, but in 3 different directions. Like if the burning cell is in the south, then we want one exit nozzle pointing, let's say the burning cell is to the south, then the exit nozzle, one is pointing to the north, one is pointing to the northwest, or in your direction it's like here, and another pointing to the northeast. Okay, for me it's west, but okay, so one is north, northwest, and northeast, if this is the south, the burning cell. Okay, so the order of operations is: first, lay out the turned off conveyor belt, but it's turned off, with its engines next to the curtain, at the point where the wind already wants to break the curtain. Then put the barrel. Then set up and direct the rest of the chimney in 45 degrees angle upwards and connect it to the barrel. The joints should be a high temperature mineral wool 2. And then turn on the barrel. The suction of the fan makes a hole in the curtain, which now acts as a funnel. Okay, so what will happen? There will be a hole here, and this will suck the air with the embers through this. The embers will be stuck here, and the hot air without embers goes to here, through all the exits. Okay, but what if the moisture released from the trees by the fire along with the soot creates a fire cloud that can even cross a river and ignite by lightning new fire spots? Then we need the last part of the solution, a lightning rod. Okay, 57 minutes. We need to do this really really fast. Okay, so now our scenario is the fire here. Here we solved the problem, but here there is a fire cloud, okay, filled with the hot soot. This is called the fire cloud. And it's coming towards, let's say here is a river. Okay, this is a river. But the fire cloud is coming across the river with the wind. I should have drawn it there because the wind is this way. But let's say now the wind is going in another way. And the fire cloud is coming. And when the fire cloud is here, then because it has all this energy inside it, and electrical charge, then it does lightning. Okay, so it makes a lightning. And this burns more trees. Okay, if there are trees here, from the other side of the river, then it will start a fire here. Okay, so we don't want the fire from here to go through the cloud and start here. So this is why we need the last part, which is the lightning rod. Okay, so now we are talking about the lightning rod. Okay, 1 hour. I need to do this verbally. I cannot draw. A normal lightning rod is passive. It waits for the lightning to come to it. Here we are active, like the famous kite experiment by Benjamin Franklin. All the links are in the video description. Okay, so kite experiment. Instead, okay, so kite experiment. In Wikipedia. Instead of a kite, we are shooting a harpoon, like this one. Notice the rope tied to the harpoon. Okay, Wikipedia, harpoon. Of course, what we are shooting is small and not pointy, so that if it falls to the ground, it wouldn't kill anybody. So we shoot the harpoon from a mortar weapon like this one, Wikipedia M224 mortar. Okay, so this is also in Wikipedia. So we have this weapon. I don't know how to draw it. Maybe it's like this. Okay, this is the ground, and here we shoot a harpoon. Okay, we have. I'm drawing it pointy, but it's not really pointy. Okay, it's like just so you understand. This is a harpoon. This is the mortar. Okay, and it has a rope, and the rope is attached to the ground. Okay, I'll explain in a moment. Okay, so this rope is attached to here. But of course, our shell is not explosive, just something to tie our rope to. The important difference is that instead of a rope, we have a copper wire. Okay, so this is a copper wire. So I will draw this in another color, which is a little red. Okay, so this is a copper wire. Like the exploding wire method to create plasma. Also in Wikipedia. Okay, so I will not have time. I hope I will read it fast. So here the fireman that operates the mortar needs to be in a safe distance, like I guess at 15 meters. Okay, so the fireman is here. And everybody should lie on the ground. I know usually the operator of the mortar is ducking next to the mortar, but for this usage, someone needs to make a remote control vice device that can open by radio signal. Okay, something that holds this until it falls and shoots. So a remote control vice that can open by radio signal, not infrared because it's hot there. because we need the operator to be in a safe distance. In order not to ruin the mortar each time, the operator anchors one side of the rope to the ground by tying it to a peg that is hammered into the ground far away from the trees. In that way, once the mortar has fired the projectile, the mortar is not connected to the rope anymore. Then he aims the mortar towards the cloud. I think a mortar can reach an altitude of about 1.5 kilometers. Okay, here is the cloud. Uh, 1.5 kilometers. It can be calculated from a parabola equation with the input of the horizontal range of the mortar, 3.5 kilometers, somehow taken into account. I'm embarrassed to say that I once knew how to calculate it, but I no longer remember, lol. Here is what a normal lightning looks like. Wikipedia, lightning, distribution and frequency. Lightning is usually produced by cumulonimbus clouds, which have bases that are typically 1 to 2 kilometers above the ground and tops up at 15 kilometers in height. So here the cloud is made of soot and smoke, etc., but I hope its lower part is in similar altitude. In any case, just like in an empty field, the lightning wants to hit the man standing because it's the highest conductor. So even if we don't quite reach up to the cloud itself, we will be the highest conductor. Okay, this harpoon will be the highest conductor with the rope. So the mortar itself should be also protected like 5 meters from the peg in the ground to which the rope is tied, in order to save the mortar in case we missed for taking another shot. Each successful shot drains some of the energy from the cloud to a safe place without trees. I think it's best if the copper wire is actually threaded inside a real rope, because otherwise the sudden pull from the projectile will tear the rope under its own weight. Okay, so I hope it will record. This was my invention. I hope it was clear, and I'll see you in my next invention. So thank you very much. Bye. Thank you.